cats and kittens. Welcome back to my YouTube channel. Today, we're going to talk about a concept called the mole. And no, we don't mean the animal. No, we don't mean the thing on your face. We mean a way of measuring particles. The mole can be an intimidating subject for new chemists especially, but when you realize it's no different than something like a dozen, it's just a quantity of measurement, it becomes a lot less scary. So when I say I have a dozen eggs or a dozen pencils, immediately you know that is 12. Or if I say I have 2 dozen pumpkins, that's 24 pumpkins. But a mole is hard for us because the number is so large. It needs to be because the atom is so small. So things at the magnitude of a mole contain not 12 particles or 12 things, but 6.022 times 10 to the power 23 things. What is that even? Well, it's 602 sextillion particles of something. It's an enormous number because even in a small sample of atoms, there are an enormous number of particles inside. To give you a flavor for it, if you had a mole, so 6.022 times 10 to the power 23, or 602 sextillion, a mole of pennies. So you were a millionaire, let's say. If you had 1 mole of pennies and you spent $1 million per second, so $1 million per second, how long do you think it would take for you to run out of money? If you were born with just a mole of pennies and you were spending $1 million per second, a year, a day, $1 million per second is a lot. Maybe 10 years, maybe less. The answer is, if you started spending $1 million per second right now, until you died at the age of 100, you would still have 99.99% of your money left over. In fact, it would take you a little bit longer than the universe has existed at spending $1 million per second just to get rid of your mole of pennies. That's how big that number is. So let's make this a little less intimidating with an analogy. This is something I like to use when we're first starting out about learning about the mole. I usually go into a big story about, oh, I live on this island, blah, blah. I'm going to spare you. But I'm going to teach you about Mole Island. It's a handy tool for you guys to be able to do any of these conversion problems you've been seeing in the video. So imagine an archipelago, a fancy way of saying an island surrounded by other islands. In this archipelago, the main central island is called Mole Island. So let's get that drawn up here now. So here we have our main island, Mole Island. And around Mole Island, we have 3 surrounding islands. One we call Mass Island, or just little g if you don't have much time. The other is Party Island, or Particle Island, if you want to be a little more formal. And the final one is Volume Island. Now, Volume Island is a little special, and we'll get to that one here in a second. But how can I travel from one island to another? Well, there's a way to get to each. To get out to Mass Island, we call it little g because we measure mass in grams. Anybody can get out there, they just have to pay a toll. There's a toll road that goes from Mass Island to Mole Island. As long as you can pay the toll, you can go out to Mass Island. And what is the toll, you might ask? Well, it depends on the weight of your vehicle. We call it the molar mass. So for example, I have my periodic table pulled up here. If I'm driving a calcium atom out there, the molar mass fee is going to be 40.08 grams per mole. If I'm driving something smaller, let's say a hydrogen atom, 1.01 grams per mole. So as long as you can pay the molar mass, you can travel back and forth from Mole Island to Mass Island. Now, to get out to Particle Island, anybody can go out there. There is a highway that connects it. The highway does have a speed limit though, 6.022 times 10 to the power 23. So a little bit faster than 26 times the speed of light, but who's checking? Now, if we want to be short, we call this number and this highway Avogadro's highway. Named after the famous scientist that first came up with this topic, this concept of a mole of a particle. You may remember it from your history project that you guys did, Amadeo Avogadro, goofy looking Italian scientist. Look him up if you have time. Now, to get up to volume island, this specifically pertains to the volume of a gas, and we can only go out here under STP days, which is standard temperature and pressure. Standard temperature happens to be 0 degrees Celsius. Standard pressure is 1 atmosphere of pressure. So about the amount of pressure you're feeling right now. Now, to get out to volume island, first we have to check, am I dealing with a gas? Yes. Is it at standard temperature and pressure? Yes. Then you can board a ferry to get out to volume island, and we call that the USS 22.4 liters. So what does all this stuff mean? It means that if I want to convert from a volume of gas, something that's actually measurable, because moles aren't really measurable directly. There's no molar scale. There's no ruler that measures moles. But we can measure volume. If I have 26 liters of a gas, and I want to figure out how many moles that is, well, I can use the relationship here. For every 22.4 liters of any gas at standard temperature and pressure, well, that's 1 mole. So if I had twice that, or 2 moles of a gas at standard temperature and pressure, it'd be 44.8 liters of that gas. And we can use this relationship to convert back and forth. The same is true for particles. If I have a sample of something, let's say 4 grams of calcium, and I want to know how many particles are in there, I can use the relationship that for every 1 mole of particles, there are 6.022 times 10 to the power 23 particles in that sample. And a particle can be anything from an atom to a molecule to a formula unit to diatomic molecules, anything really. The final relationship is the one we'll probably use most frequently, and that's between mass, or grams, and moles. Because mass is so easy to measure. We just slap something on a scale, we measure its mass, we know what it is in grams, and we can simply convert that to moles, so long as we know the molar mass of whatever particle we have in question. As we said previously, if you have a sample of calcium, 40.08 grams of calcium on a scale, so I measure it out, 40.08 grams, that would be 1 mole. And I can traverse back and forth between those. Now notice on this, there is no quick way to connect from grams to particles, or grams to volume, or volume to particles, or volume to grams. You have to go through the mole to get there. So in a moment, I'm going to show you a few problems with a much more simplified drawing, but if you want to get this down, I think it could be of great use to you. And then I'll show you a simpler version here in a second. So I'll give you a second here. Okay, let's take a look at what a few problems might look like, some that you may have seen from the video. Hopefully we can demystify those a little bit and make them a little easier for you to do. So I'm going to draw real quick my island reference just off to the side. I know that I have mole island, which we abbreviate MOL. I'm not sure why leaving the E off makes it easier, but that's what we do. Up here we have mass island, which is measured in grams always. We know we can connect those two with the molar mass, which can be found on the periodic table. We have particle island, which can be anything from atoms to molecules to formula units if we're dealing with ionic compounds. And we use Avogadro's highway, his number to get out there, 6.022 times 10 to the power 23. Now in a lot of videos you see this number as 6.02, simply 10 to the power 23. It makes no difference which one you use. 6.022 is a little bit more accurate. It's what I tend to use when I teach AP Chem, but the true number is even a bit longer than that. And you might say, well, what does it really matter? Well, remember the magnitude of this number. That's not a 0.022. We're raising it to the power 23. So this 2 represents trillions and trillions of particles. Now, the final one, volume island, we know we have to take a special boat to get out there, and that's the USS 22.4 liters. With this simple drawing, you should be able to complete almost any problem. So let's take a look at what something simple might look like. Let's say I have 24.9 mole of potassium. And I want to know how many grams is that sample. The first thing I'm going to do is I'm going to bring directly down the units I'm given in the problem. It seems like I'm rewriting this over, and I am. So 24.9 mole potassium. We're going to use dimensional analysis to solve these. So I want to see, where am I at right now on my island? I'm at the mole. The problem's asking me to get out to grams. How do I go from moles to grams? Well, I use the molar mass. I check the periodic table and I see that for potassium, it's 39.1. So if I have 39.1 grams of potassium, I have 1 mole of it. In looking at this, I can already tell that I have a little less than a mole, so my number should come out to be something less than 1. So I have mole now, so I want mole in the denominator of my fraction. So I know for every 1 mole of potassium, there are 39.1 grams. The moles cancel for me, and now it's just a problem for your calculator. Remember, the top of a fraction means multiply, the bottom means divide. So we are dividing here, but we're dividing by 1, so we don't really need to do that. So I have 24.9 times 39. And I come out with 973.59 grams. Now, 2 things. One, I look and I see the problem had 3 significant digits, so my number really should only have 3. I look, the 3 is the third one, 5 is behind it, that rounds it up to 974 grams of potassium. That would be my final answer. Also, at the beginning of this whole mess, I misspoke because I wasn't looking at my units very carefully. We're not starting at the units of gram, we started at the units of moles. And because we have more than 1 mole, in fact, we have almost 25 moles, we should expect that we would have significantly more than the molar mass of potassium, which was 39.1. So if we had only 1 mole of potassium, we'd only have 39.1 grams. If we had 2 moles, we'd have what? About 80 grams, a little less. So sorry about that. Here's a simple problem. Let's take a look at one that's a little bit trickier. All right, let's look at one that's multiple steps. So imagine we have the following situation. It's difficult to measure the mass of a gas. How do you make the gas go onto a scale? Well, we can use a process of stoichiometry to do this. So imagine that I have a balloon that I know is filled with exactly 2.4 liters of oxygen. And I want to know, how much does that oxygen weigh? What is its mass? I'm not being very careful here about the difference between mass and weight. Please know that there is one. You can look that up and explore it on your own time. But let's say I have my balloon and I want to figure out what is the mass of the gas inside the balloon. So I have a 2.4 liter balloon filled with oxygen. Now, if I just say oxygen and don't specify, remember that oxygen is a diatomic molecule. It's one of the Brinkelhoffs, or the 7 that make a 7. So all the oxygen you're breathing in now isn't just O, it's O2. And I want to know, how much mass is that? Well, let's draw a road map here and figure out how can I go from one island to another. I'm starting here at Volume Island. Please note that the volume has to be measured in liters. If you're given something else like milliliters or deciliters or kiloliters, you can of course use your metric conversions to go 2 liters, the basic unit. Now, I want to turn this into grams. This is my end point, but I can't go directly there. I have to turn this into moles first, and then I have to turn the moles into grams. This problem will be 2 steps. And I know that because I'm crossing 2 bridges to get to my final destination, which means I'll have 2 fractions, 2 conversion factors in my dimensional analysis. So let's set the problem up. In solving these guys, you always want to be right rather than being quick and wrong. These problems can take a while no matter what you do, so there's no sense in trying to shortcut it, to be honest. So I'm going to bring down directly what I've been given, 2.4 liters of oxygen. I know I need to turn those liters into moles first. The unit I'm starting in is liters, so I want to cancel liters. I know that if I have 22.4 liters of any gas at standard temperature and pressure, that's 1 mole. So I need to turn it into moles first. So whatever I'm turning it into, wherever I'm going, I put on the top of my fraction. So 1 mole. For every 1 mole of any gas, there are 22.4 liters. Now that brings me to the main central island, Mole Island. The final step will be turning this into grams. So I use my periodic table and I see that atomic oxygen has a molar mass of 16. This is molecular oxygen, O2. So there are 2 oxygen atoms here. So it has a molecular mass of 32 grams per mole. I want to go 2 grams, so I put 32 grams on top, 1 mole on bottom. If we've been cautious, the units that cancel, mole and liters, should leave remaining only the ones we want, our destination, grams. And we see that we have grams of O2. That's exactly what I want. So now I go through and solve in my calculator, remembering that the denominator means divide, the numerator means multiply. So I have 2.4 divided by 22.4 times 32. And I end up with 3.428. grams. Checking my sig figs, there are 2 here, so I only want 2 in my answer. The 4 is the second significant digit. The number after it is a 2, so we don't round up. 3.4 grams O2. And that is our final answer. All right, let's check our final problem now. This one we're going to use Avogadro's number. This one can be tricky for you, not because you don't know what you're doing, but because your calculator will betray you if you're not careful. Remember, when in doubt, just use the parentheses. Tell the calculator what to do. Don't let it make its own decisions. So let's say we have the following problem. I have a sample of sodium chloride, table salt, and I want to figure out how many individual particles are in my sample of table salt. You could do this at home. Measure out your table salt. You can put it on a kitchen scale. Let's say I measure it out and I have a sample of 1.68 grams of sodium chloride, NaCl. And I want to know, how many formula units is that? I'm using the term formula units because table salt is an ionic compound, a metal and a non-metal that have undergone electron transfer, held together with electrostatic attraction. So let's draw out our roadmap. I'm starting at grams, so I'm here at mass island, and I want to get to formula units, which is a kind of particle. Can you remember, going from grams to moles requires the molar mass. Then, once we go from moles to particles, we'll need Avogadro's number. So let's take this one step at a time. First, I'm going to bring down exactly what I'm given, 1.68 grams sodium chloride. My first step, I need to turn these grams into moles. Where I'm going, I want to put on top, so 1 mole. Now I need to find the molar mass of sodium chloride. I add the two molar masses together. I see that in this formula unit, there's one atom of each. The molar mass of sodium on its own is 22.99. The molar mass of chlorine is 35.45. So the molar mass overall is 58.44. That will cancel out the grams for me. And if I look along the way, it tells me where I am. I went from grams to moles. So I'm on mole island. The final step now is to turn this into formula units, or number of particles. So I'm going 2 particles, so I want to use Avogadro's number on top, 6.022 times 10 to the power 23. My particle in question this time is the formula unit. And I want to cancel out the moles, that's where I'm coming from. So I put that on bottom, and the moles cancel. Just as before, we're going to go through and compute this now. 1.68 divided by 58.44 times Avogadro's number now. We'll use parentheses to be careful. 6.022 times 10 to the power 23. Close our parentheses. And we end up with 1.73 times 10 to the power 22. And I've already rounded this off for sig figs for you guys. That's our final answer. Now, there are a variety of problems like this. It just takes practice, practice, practice. I wanted to give you guys my methodology, but there are a ton of other ones. Search them up on YouTube. Use the keywords like stoichiometry, the mole conversion problems. You'll be able to find a plethora of other examples, and I'll be working some from your homework as well this week. Please send me any questions you have over in mind, and we'll see you back here next time.